Welcome once more to the dark. Picture a sphere 2 billion light-years wide, its edges traced not by walls but by the rising tide of galaxies that suddenly appear when you look far enough out. Inside, the stars are still there, the clusters still hang in their appointed places, but the counts keep coming up short. For every 2 galaxies the standard model expects, only one is here. The pattern shows up in radio, infrared, X-ray, optical, every wavelength they have mapped. The galaxies are simply not there. Tonight I want to show you the hole we have been living inside all along, and why it may be the reason the universe seems to keep 2 different times. Before we begin, if this journey into the quiet spaces between galaxies stirs something in you, leave a small light behind, a like, a subscription, so others may find their way here too. Now settle in, dim the lights if you haven't already, let your breath slow. We're going to map something enormous tonight, something that wraps around us on every side. You don't need to hold on to every detail, just let the images arrive, one by one, while you drift. We're going to trace the edges of a hole 2 billion light-years wide, and then ask why no one expected it to be there. I am the cartographer of the dark, and I have been mapping these distant places for longer than I can remember. You and I are travelers together through the same emptiness, and tonight we trace the borders of the sparser bubble we call home. Before we learned to count galaxies in every direction, cosmology rested on a single beautiful assumption. It was called the cosmological principle, and it said something simple: that the universe, viewed on large enough scales, looks the same everywhere. No special places, no center, no edge, just a vast, patient uniformity stretching in every direction, the same from every vantage point. This was not wishful thinking. It was the foundation of the standard model of cosmology, the framework we call lambda CDM, and for decades, every measurement seemed to confirm it. The universe is approximately 13.8 billion years old. The observable portion spans about 93 billion light-years from edge to edge, a sphere of light whose boundary marks not a wall but simply the distance light has had time to travel since the beginning. Within that sphere, the standard model predicted smoothness. Not perfect uniformity. Gravity had been at work for billions of years, pulling matter into galaxies, clusters, filaments, the great cosmic web, but smoothness in the average. On scales of a few 100 million light-years, the model said, one neighborhood should look much like any other. Variations of only about 3% from place to place. A universe almost perfectly blended. The evidence for this smoothness came from the earliest light we can see. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and light streamed freely for the first time. That light, stretched by expansion into microwaves, still fills the sky. We call it the cosmic microwave background. Satellites have measured its temperature in every direction, and the variations are astonishingly small, only about 1 part in 100,000. The early universe was extraordinarily smooth, almost featureless, a canvas of nearly uniform density waiting for gravity to sketch the first structures. From those tiny seed fluctuations, the cosmic web grew. Denser patches pulled in more matter, galaxies formed, they gathered into clusters, clusters lined up along filaments. Between the filaments, voids opened, regions where galaxies are sparse, where matter drained away toward the denser scaffolding. This was expected. Voids are a natural feature of cosmic structure, predicted by the standard model and seen in simulations. But the model also set a limit. The largest void should not exceed a certain size, a ceiling imposed by the shape of the initial fluctuations, by the power spectrum that describes how much lumpiness exists at each scale. That power spectrum is well measured. It follows a form first proposed in the early 1970s, a scale invariant pattern that cosmologists call Harrison-Zeldovich. The cosmic microwave background gives us the normalization, the overall amplitude of the fluctuations. Run those numbers forward through 13.8 billion years of gravity, and the model tells you how smooth the universe should be today. On a scale of 300 million light-years, the root mean square density variation should be only about 3.2%. For every 100 regions you sample, the densest might hold 103% of the average number of galaxies, the sparsest about 97%. The universe should be nearly uniform, a gently textured expanse with no dramatic holes, no vast deserts where galaxies simply fail to appear. This was the expectation. The cosmological principle, encoded in equations, tested against the microwave sky, woven into every calculation of cosmic history. The universe looks the same in every direction. The universe looks the same from every location, homogeneous and isotropic, the textbooks said. A smooth universe, at least when you step back far enough to see the whole. Astronomers began counting galaxies to test this. Not by eye, there are too many, but systematically, using surveys that map the heavens in different kinds of light. Near-infrared light, around 2.2 micrometers wavelength, traces the mass of stars more reliably than visible light. Dust does not dim it much. The corrections needed to compare galaxies at different distances are small, so near-infrared surveys became the standard tool for mapping cosmic density. One such survey, called the 2-micron all-sky survey, imaged the entire sky and published its catalogue in 2006. Another, the UK IDSS Large Area Survey, went deeper over a smaller patch, capturing tens of thousands of galaxies. These catalogues were combined with redshift measurements from the Sloan Digital Sky Survey, the 2-micron all-sky redshift survey, and the 6-degree field galaxy redshift survey. Together, these datasets covered about 90% of the sky and reached depths sufficient to map the density of galaxies out to distances of several 100 million light-years. The method is straightforward. Count how many galaxies appear in each shell of distance. Divide by the volume of that shell. Compare the results to the cosmic average. A density contrast describes the difference. 0 means average density. 0.5 means the region holds only half the expected number of galaxies. 1 would mean total emptiness, though such a void does not exist. The standard model, with its 3% variations, predicts the contrast should rarely exceed 0.1 on large scales. A 10% underdensity here, a 10% overdensity there, but nothing dramatic. No one expected the counts to come up short everywhere at once. No one predicted that our local neighborhood, extending out hundreds of millions of light-years in every direction, would hold only about half the galaxies the standard model says should be there. But that is what the surveys found. The pattern showed up no matter which kind of light astronomers used to look: radio, infrared, X-ray, optical. The galaxies were simply not there. For every 2 galaxies the average region of the universe contains, our local neighborhood holds only about 1. The density contrast, measured across multiple independent surveys, settled around 0.46, roughly half empty. Not a small fluctuation. A deficit 15 times deeper than the standard model allows on this scale. The universe at this scale should be smoothed to within 3% of perfection. Instead, we find ourselves inside a hole that is almost half empty, a sparser than average bubble, stretching outward in every direction, reaching the cosmic mean density only at a distance of roughly 500 million light-years. Beyond that distance, the density of galaxies is what the standard model predicts. Closer in, the counts fall short. The structure has come to be called the KBC void, named after the 3 astronomers who published the definitive measurement in 2013, though hints of it had appeared in galaxy surveys as far back as 1990. It is one of the largest known cosmic underdensities, with an overall diameter clustering around 600 million parsecs, roughly 2 billion light-years. The Milky Way, the local group of galaxies, the wider Laniakea supercluster, all of it lies inside, and we sit near the center. Not by choice, not by design, but by the constraint of another measurement. The cosmic microwave background shows a dipole pattern. One hemisphere slightly warmer, the other slightly cooler. Because the Milky Way is moving at 627 kilometers per second relative to the rest frame of the early universe. That motion is a peculiar velocity, the result of gravitational tugs from nearby structure. If we were far from the center of the void, that velocity would be much larger. The smallness of the dipole tells us we must be near the middle, a quieter spot, a sparser bubble, a neighborhood where, for reasons the standard model struggles to explain, fewer galaxies ever formed. The cosmological principle said there should be no such place. The power spectrum said fluctuations this deep should not exist on scales this large. The simulations, run with billions of dark matter particles across boxes spanning billions of light-years, sampled 1 million random vantage points and found that a density contrast of 0.46 on a 300 million light-year scale occurs, with a probability so low it would take many universes to find one. The standard model did not forbid voids, it forbade this void, this size, this depth, this location, with us sitting quietly near its center. The cosmological principle was an assumption, elegant and powerful, that let us model the whole cosmos with a handful of equations. It said that our corner of the universe is ordinary, that on the larger scales, every neighborhood looks like every other. Then we started counting galaxies, in every direction and in every kind of light, and the counts kept coming up short. The smooth universe we expected, the one written into the equations, the one encoded in the microwave background, the one that should vary by only 3% from place to place, does not match the universe we measure around us. We appear to live in a hole, a vast underdensity, a bubble of emptiness 2 billion light-years wide. And no one told us, because no one knew, because the standard model said it should not be there. We wonder sometimes who is listening tonight. From what city, what hemisphere, what corner of the turning Earth. The stars look different from every place we stand. If you feel like it, leave your city below. We're curious where this finds you. To map the universe is to count. Not stars one by one, but galaxies by the thousands. Their light sorted and catalogued, their distances measured, their positions plotted against the black. For a century, astronomers assumed the work would be straightforward. The cosmological principle promised that every region, viewed on large enough scales, would look like every other. And so the task became simple repetition. Point the telescope, count what you see, move to the next patch of sky, and count again. The numbers everyone expected would come out the same. They did not. The first challenge was deciding what to count. Galaxies shine in many colors, and not all light travels equally well across the universe. Dust between the stars absorbs blue and visible light, dimming distant galaxies and making them harder to see. But near-infrared light, the kind that glows around 2.2 micrometers in wavelength, cuts through most of that complexity. It traces the mass of stars directly. Dust barely touches it. The corrections needed to compare galaxies at different distances become small, weakly dependent on the details of each galaxy's history. And so near-infrared light, specifically the band astronomers call K-band, became the ruler by which the local universe would be measured. The 2-micron all-sky survey, published in 2006, was the first complete map of the whole sky in this wavelength. Its extended source catalog became the foundation. Every galaxy bright enough to be seen, cataloged. Every direction covered. The survey did not measure distances directly, only brightness and position. But other projects filled that gap. The 2M++ catalog combined the infrared brightness measurements from 2MASS with spectroscopic redshifts drawn from 3 large surveys. the Sloan Digital Sky Survey, the 2-mass redshift survey, and the 6-degree field galaxy redshift survey. Together, they covered roughly 90% of the sky, nearly complete out to a limiting brightness, reaching tens of thousands of galaxies. For the first time, astronomers could see not just where galaxies sat on the sky, but how far away they were, how their numbers changed with distance, whether the density of matter around us matched the density of matter farther out. A smaller survey called UKIDSS, the United Kingdom Infrared Deep Sky Survey Large Area Survey, went deeper. It covered less sky, only about 585 square degrees, but it pushed to fainter galaxies, nearly complete to a brightness 3 magnitudes dimmer than 2M++. 35,000 galaxies in its primary sample, each with a measured redshift, each a tracer of the underlying mass. The two catalogs, shallow and wide versus deep and narrow, would check each other. If the universe was smooth, the galaxy counts per unit volume should stay constant as you look farther out. Density is measured as a contrast, a fraction missing. If a region holds the average number of galaxies, the contrast is 0. If it holds half the expected number, the contrast is 0.5. For every 2 galaxies the standard model expects, only 1 is there. The cosmological principle predicted the contrast should be close to 0 everywhere, once you average over large enough volumes. On a scale of 300 megaparsecs, the standard model predicted the universe should look almost perfectly smooth, variations of only about 3% from one place to another. The measurements told a different story. The K-band luminosity density, the amount of starlight per unit volume, was not constant. Nearby, within a redshift of 0.07, corresponding to a distance of roughly 300 megaparsecs, the density sat below the cosmic average. But beyond that distance, beyond a redshift of about 0.1, the density climbed. Galaxies became more common. The universe farther out was brighter, more crowded, denser. The difference was not subtle. Beyond the threshold, the luminosity density was approximately 1.5 times higher than the value measured locally. For every 2 galaxies in an average patch of the universe, our local neighborhood held only about 1. The shape of the galaxy population did not change with distance. Bright galaxies and faint galaxies appeared in the same proportions nearby and far away. That ruled out the possibility that the difference was an artifact of galaxy evolution, some systematic error in how astronomers were counting. The rising density was genuine. The local universe was not average, it was sparse. The deeper subsample of the 2M++ catalog, covering regions where the Sloan and 6-degree field surveys overlapped, sharpened the picture. Between a redshift of 0.01, about 40 megaparsecs, and 0.07, about 300 megaparsecs, the density contrast measured 0.46, with an uncertainty of 0.06. The local region contained roughly 54% of the matter it should. The deficit was consistent across independent samples, across different parts of the sky, across surveys that used different telescopes and different methods to measure redshifts. And the pattern showed up no matter which kind of light astronomers used to look. Radio surveys counted galaxies emitting at centimeter wavelengths and found the same underdensity. X-ray surveys mapped clusters of galaxies, the largest gravitationally bound structures in the universe, and found 15 to 30% fewer clusters within about 100 megaparsecs than the model predicted. Optical surveys, infrared surveys, every wavelength told the same story. The galaxies were simply not there. The K-band luminosity density reached the cosmic mean at roughly 500 megaparsecs from us. Beyond that distance, the density of galaxies matched what the standard model predicted. The universe farther out looked ordinary. The deficit was local. Estimates of the overall diameter of the underdense region clustered around 600 megaparsecs. roughly 2 billion light-years, making it one of the largest known cosmic underdensities. And we sat near the center. That placement was not an assumption, it was a requirement. If the Milky Way were far off to one side of the void, we would see more galaxies in one direction than the other. The cosmic microwave background would show a corresponding asymmetry far larger than what is observed. The smallness of that asymmetry constrains where we can be. The data allow only one conclusion. The Milky Way sits near the center of the void. The sparser-than-average bubble surrounds us almost symmetrically. The local group moves at 627 kilometers per second, relative to the cosmic microwave background. A peculiar velocity consistent with our location inside a region of below-average density. The denser universe beyond pulls us outward. The void does not trap us in the sense of gravity holding us in place. It is not a pit. It is a bubble, and we drift within it, carried by the same expansion that stretches all of space, nudged gently by the gravitational pull of the matter we are moving toward. No one expected this. The universe on this scale should look smooth. The early universe, imprinted in the cosmic microwave background 380,000 years after the beginning, showed temperature variations of only 1 part in 100,000. Gravity amplified those tiny seeds over billions of years, pulling matter together into clusters and filaments, leaving voids in between. But the largest voids should not exceed the size predicted by the initial fluctuations. The power spectrum of those fluctuations, measured precisely by the Planck satellite, allows for density variations of only about 3% on a 300 megaparsec scale. The observed value, almost 50%, is roughly 15 times deeper. And yet the void is there. Measured independently by teams using different catalogs, different wavelengths, different statistical methods. The agreement is not perfect, but the direction is unanimous. Our corner of the universe holds fewer galaxies in every direction than the model says it should. The counts kept coming up short, and no one for a very long time told us we were living inside a hole. For 30 years the clues arrived quietly, scattered across wavelengths and catalogs and hemispheres of sky, each one a whisper that something about our neighborhood was not quite what the textbooks predicted. In the early 1990s, optical surveys of galaxies across the southern sky began to show a pattern no one had asked them to find. The counts came back lower than expected. Maddox and his colleagues, tallying galaxies visible in ordinary light, noted the shortfall but could not yet say whether it was real or merely an artifact of dust, of selection, of the instruments themselves. Through the rest of that decade, the hint sharpened. Huang and Zucker, working independently with near-infrared and optical catalogs, reported underdensities in the local universe, regions where galaxies seemed fewer than the cosmic average. The measurements were tentative, the samples small, but the direction was consistent. By 2003, the pattern had a name. Frith, Buswell, Fong, Metcalf and Shanks analyzed the 2-micron all-sky survey, a complete infrared map of the entire sky, and found a deficit of galaxies stretching across both the northern and southern galactic caps. In the south, the shortfall reached 30%. In the north 18%. The scale was enormous, a region roughly 500 million light-years across, and the team called it the local hole. The emptiness did not go away. A decade later, Whitbourne and Shanks extended the analysis, folding in redshift measurements from 3 major galaxy surveys, mapping the distribution of matter not just across the sky, but outward, in depth, shell by shell. They concluded that the local group inhabits a genuine underdensity in the large-scale structure of the universe. The deficit was deepest in the southern galactic cap, reaching 40% in some directions, and it persisted consistently out to a distance of roughly 500 million light-years. For every 10 galaxies the standard model expected, only 6 or 7 were there. In 2022, Wong, Shanks, Metcalf, and Whitbourne pushed the survey coverage to 90% of the sky. They found an underdensity of 21 to 22% within a sphere encompassing everything closer than about 300 million light-years. The deviation from the predictions of the standard cosmological model stood at nearly 3 standard deviations. The hole, if that is what it was, covered almost the entire local volume. And then came a measurement that made the picture stranger still. Karachentsev, studying the matter density within a smaller sphere, roughly 160 million light-years across and centered on the local group, found that the total mass per unit volume in our immediate cosmic neighborhood is only about a quarter of the global cosmic value. For every 4 parts of matter the universe holds on average, our region holds only 1. The measurement was independent of galaxy counts. It looked directly at the gravitational mass, the dark matter and the luminous matter together, and found the same deficit. What made the local hole difficult to dismiss was not any single measurement, but the agreement across methods. The pattern showed up no matter which kind of light astronomers used to look. Radio surveys of distant galaxies, catalogs built from X-ray emissions of galaxy clusters, optical and infrared star counts, all pointed to the same conclusion. The galaxies were simply not there. Rubart and Schwartz, scanning the sky in radio wavelengths, found the underdensity. Bengali and colleagues confirmed it independently. Boringer's team, mapping galaxy clusters by their X-ray glow in the reflex and classics surveys, measured a 15 to 30% matter deficit within a sphere roughly 300 million light-years wide. The void was not a trick of one telescope or one team. It was written into the architecture of the local universe. The cosmological principle, the assumption that every neighborhood of the universe looks like every other when viewed on large enough scales, had always rested on a kind of modesty. We are not special. Our location is ordinary. The universe, smoothed over a few 100 million light-years, should look the same here as it does anywhere else. The cosmic microwave background, released when the universe was only 380,000 years old, shows temperature variations of only about 1 part in 100,000. The early universe was extraordinarily smooth. Structures grew over billions of years from those tiny fluctuations, pulled together by gravity into the cosmic web of clusters, filaments, and voids. But the standard model, built on that early smoothness, predicts that the universe at this scale should still be smoothed to within about 3% of perfection. And instead we find ourselves inside a hole that holds only about half the galaxies it should. No one expected a structure this deep on this scale. The hint had been there since the first optical counts in 1990, but the full picture took 3 decades to assemble. By the time Keenan, Barger, and Cowie published their landmark measurement in 2013, the underdensity had been detected across the electromagnetic spectrum, confirmed by independent teams, and mapped in 3 dimensions. The local hole was no longer a marginal feature in a single catalogue. It was a sparser-than-average bubble, roughly 2 billion light-years wide, and we live somewhere near its center. Near-infrared light, at wavelengths around 2.2 micrometers, traces the mass of stars more directly than visible light does. Dust does not dim it much, and the corrections needed to compare galaxies at different distances are small. The 2-micron all-sky survey, published in 2006, provided a complete infrared map of the sky. Its extended source catalog became the foundation for most local density measurements. The 2M++ catalog, assembled by Laveau and Hudson, combined that infrared photometry with redshift measurements from the Sloan Digital Sky Survey, the 2-micron all-sky redshift survey, and the 6-degree field galaxy redshift survey. It covered 90% of the sky and was 98% complete to a carefully chosen brightness limit. Every survey pointed to the same conclusion. Beyond a certain distance, galaxies become roughly 50% more common than they are around us. The transition is not sudden. The density rises gradually as you look outward, reaching the cosmic average at roughly 500 million light-years from the Milky Way. Beyond that distance, the density of galaxies is what the Standard Model predicts. Inside that boundary, we are in a quieter neighborhood. The shape of the galaxy population does not change with distance. The distribution of bright galaxies and faint galaxies, massive galaxies and dwarf galaxies, remains constant as you look outward through the void. That constancy is important. It means the rising density is genuine, not an artifact of how galaxies evolve, or how we measure them. The whole is not a trick of the instruments. It is simply fewer galaxies in every direction, all the way out to the edge. And yet the cosmological principle says this should not be possible. The power spectrum of density fluctuations, measured with exquisite precision by the Planck satellite, and traced forward through 13.8 billion years of cosmic evolution, predicts root mean square variations of only about 3% on a 300 million light-year scale. The observed deficit is 15 times deeper than that. For every 2 galaxies the average region of the universe contains, our local neighborhood holds only about 1. The local hole is not the only void in the universe. The cosmic web is laced with them, vast regions of near emptiness, bounded by filaments and clusters where galaxies congregate. But most voids are smaller, and none of the well-mapped voids sit so strangely close to us. There is a smaller structure nearby, a separate underdensity about 200 million light-years across, called the local void, mapped by Tully and Fisher in the 1980s. That void lies adjacent to us, not around us. The local hole is something larger. It is one of the largest known cosmic underdensities, and the Milky Way, the local group, and the wider Laniakea supercluster all lie inside it. The measurements do not tell us we are at the exact center of the void, but they do tell us we are near it. If we were far from the center, the underdensity would look lopsided. Counts in one direction would fall short, while counts in another would rise to meet the cosmic average. Instead, the deficit is nearly symmetric across the sky. The pattern is consistent with a location near the center of the bubble. That nearness is itself strange. The cosmological principle does not merely say that voids exist. It says that we should not occupy a special place within one. To find ourselves near the center of an underdensity this large is, by itself, a puzzle. And the void may explain something even stranger. The local group moves at 627 kilometers per second relative to the cosmic microwave background, a peculiar velocity measured by Kogut and his colleagues in 1993. That motion is consistent with our location inside a sparser-than-average region. If the matter around us is less dense than the universe at large, the gravitational pull from the denser surroundings beyond the void's edge would drag us, and everything nearby, outward. For 30 years the hints accumulated, galaxy counts in optical light, in infrared, in radio, in X-ray, redshift surveys covering 90% of the sky, matter density measurements within 50 million parsecs, within 100, within 300. Every measurement pointed to the same sparser bubble, the same quiet neighborhood, the same deficit of galaxies stretching outward in every direction. The local hole was no longer a hypothesis. It was a feature of the local universe, mapped and measured and confirmed. The cosmological principle had stood unchallenged for decades. On the larger scales, the universe should look the same in every direction and from every location. Smooth, homogeneous, isotropic. The Standard Model rested on this assumption the way a cathedral rests on bedrock. And for most of the 20th century, the assumption held. Galaxy surveys were shallow, incomplete, patchy. The evidence was consistent with smoothness because there was not yet enough evidence to say otherwise. Then astronomers began counting galaxies in the near-infrared, where dust does not hide them, and the corrections needed to compare one distance to another are small and well understood. They used the 2-micron all-sky survey, a complete map of the whole sky published in 2006, and its descendants, catalogs that combined infrared light with spectroscopic redshifts measured by the Sloan Digital Sky Survey, the 2-micron all-sky redshift survey, the 6-degree field galaxy redshift survey. The catalogs grew deeper, the counts grew more precise, and a pattern began to emerge. In the early 2000s, hints of a local underdensity appeared in the literature. Optical galaxy counts in 1990 suggested fewer galaxies nearby than farther out. Studies through the 1990s and early 2000s sharpened the hint. In 2003, a team led by William Frith analyzed the 2-micron all-sky survey extended source catalog, and found a deficit of galaxies in both the southern and northern galactic caps, roughly 30% fewer in the south, 18% fewer in the north, on a scale stretching out to about 150 megaparsecs. They called the feature the local hole. The name stuck. Over the next decade, independent teams using independent methods found the same deficit. It showed up in radio galaxy counts, in X-ray surveys of galaxy clusters, in optical light, in infrared light. The galaxies were simply not there. No matter which kind of light was used to look, the pattern held. Our neighborhood appeared sparser than the universe at large. No one expected what came next. In September 2013, Ryan Keenan, Amy Barger, and Lennox Cowie published a paper in the Astrophysical Journal that gave the structure its modern name and its first rigorous measurement. They had taken the UK Infrared Deep Sky Survey Large Area Survey, a deep infrared catalogue covering 585 square degrees of sky, and combined it with the shallower but wider 2-micron++ catalogue at nearby distances, and the Galaxy and Mass Assembly Survey at the faint end. Together, the dataset spanned a range of redshifts from 0.005 to 0.2, corresponding to radial distances from roughly 50 megaparsecs out to 800 megaparsecs, a sweep that carried the count from our immediate surroundings all the way out past the edge of what would come to be called the KBC void. They measured the density of galaxies as a function of distance by counting how much light those galaxies emitted in the infrared K-band, a wavelength that traces the mass locked up in stars. They divided the sky into shells, each shell a little farther from us than the last, and they counted the galaxies in each shell and added up their light. What they found was this: beyond a certain distance, galaxies become roughly 50% more common than they are around us. The transition happens at a redshift of about 0.1, corresponding to a distance of roughly 300 megaparsecs. Closer than that, the density of galaxies sits below the cosmic average. Farther than that, the density rises and holds steady at the value the Standard Model predicts. The shape of the galaxy population, the mix of bright galaxies and faint galaxies, the distribution of masses, remains constant with distance. The rising density is not an artifact of galaxy evolution or a trick of the light. It is a genuine change in the number of galaxies per unit volume. The measurement itself was clean. The UK Infrared Deep Sky Survey sample contained 35,342 galaxies, 95% spectroscopically complete to an infrared magnitude limit that reached faint enough to trace the density out to redshift 0.2. The 2-micron++ catalogue covered roughly 90% of the sky and was 98% complete to its own limiting magnitude. The overlap between the datasets allowed the team to check for systematic errors. The counts agreed. The deficit was real. They quantified it using a standard measure that describes how many galaxies of a given brightness exist per unit volume. Beyond redshift 0.09, that number was roughly 1.4 times higher than the value measured locally, at redshifts below 0.07. In plain language, for every 10 galaxies the standard model expects in our neighborhood, the universe farther out contains 14. The void was not empty. It was not a bubble of nothing. It was a region where galaxies are sparser than average, where the cosmic web is stretched a little thinner, where the filaments connecting clusters of galaxies are a little farther apart. A traveler moving outward from the Milky Way would not notice a boundary. There is no edge, no wall, no sudden drop. The density rises gradually, shell by shell, until it reaches the cosmic mean at a distance of roughly 500 megaparsecs. But the deficit is deep enough, and wide enough, that it should not exist. The standard model, fed the initial conditions measured by the Planck satellite in the cosmic microwave background, predicts that on a scale of 300 megaparsecs, the universe should vary by only about 3% from one place to another. The observed deficit is not 3%, it is closer to 50%. The universe at this scale should be smoothed to within a whisper of perfection, and instead we find ourselves inside a region that holds only about half the galaxies it should. Keenan, Barger and Cowie noted explicitly in their paper that an underdensity of roughly this size and depth would, by itself, be enough to make the universe's two clocks disagree. They were referring to the Hubble constant, the number that measures how fast the universe is expanding today. Two precise methods of measuring that constant had been drifting apart for years, and by 2013 the disagreement had grown too large to ignore. The authors suggested that if we live inside a hole in the galaxy distribution, the galaxies around the hole's edge would be falling outward, pulled by the denser universe beyond. Their light would look more red-shifted than it should. Our measurement of how fast the universe is expanding would come out higher than the true cosmic mean value. The paper did not prove the connection. It pointed at it. It said, here is a hole, and here is a tension, and the size of the hole matches the size of the tension. The KBC void entered the literature as a hypothesis in need of testing. The deficit extends in all directions. It is not confined to one patch of sky. It is not a quirk of the Milky Way's location within the local group, or the local group's location within the Virgo supercluster. It is a feature of the large-scale structure itself, a sparser-than-average bubble centered, as far as the data can tell, very close to where we sit. The paper appeared in the Astrophysical Journal in 2013, volume 775, page 62. Follow-up studies using different catalogs, different wavelengths, different statistical methods have confirmed the deficit. Some have refined the measurement. Some have questioned the interpretation. None have made the deficit go away. Over the next decade, the tests came. Teams measured the density of galaxies in radio light, in X-ray light, in optical light. They counted galaxy clusters. They measured the peculiar velocity of the local group relative to the cosmic microwave background. They ran cosmological simulations and asked how often a structure this large and this deep should appear in a universe governed by the standard model. The answers pointed in the same direction. The void is real, and it is larger than the standard model comfortably allows. Keenan, Barger and Cowie had mapped the emptiness we call home. They had counted the galaxies in every direction and found the counts coming up short. They had measured the scale of the deficit and found it stretching out to distances where the cosmological principle promised uniformity. And they had noted quietly that the whole might explain why the universe's two clocks refused to agree. The discovery did not resolve the tension. It opened a new chapter in the effort to understand it. The void became a piece of the puzzle, a clue that pointed towards something deeper. Whether that something is a flaw in the standard model, or new physics hiding in the expansion history of the universe, or simply an unlikely fluctuation that happened to land where we could measure it, remains an open question. But the counts are in, the density contrast is measured, the local hole is no longer a hint in scattered papers from the 1990s. It is a structure with a name, a size, a depth, and a place in the cosmological conversation. And it sits, quiet and vast, around the only vantage point from which we have ever looked out at the universe. We have measured the emptiness, and the emptiness has dimensions. The cosmological principle promised us that the universe, viewed from any location on a large enough scale, should look essentially the same. Density should vary by only a few percent from one place to another. The standard model, tuned to match the exquisite smoothness of the cosmic microwave background, predicts that across a sphere 300 megaparsecs wide, the number of galaxies should fluctuate by no more than 3%. The universe at this scale should be smoothed to within 3% of perfection, a tapestry woven so evenly that no thread stands out, no patch runs thin. No one expected what the galaxy counts revealed. When astronomers adopted the deeper subsample of the 2M++ catalog, covering the regions mapped by the Sloan Digital Sky Survey and the 6-degree Field Galaxy Redshift Survey, and measured the density of galaxies in near-infrared light across a range of distances, they found a deficit that began close to home and extended outward for hundreds of millions of light-years. Between a distance of roughly 40 megaparsecs and 300 megaparsecs from us, the local region contains only about half as much luminous matter per unit volume as the universe further out. The density contrast came out to 0.46, plus or minus 0.06. Translated into plain language, that means for every 2 galaxies the average region of the universe contains, our local neighborhood holds only about 1. The void is not empty. It is sparse. Galaxies still populate the space around us, still gather into groups and clusters, still trace the filaments of the cosmic web. But they do so at roughly half the rate they should. The Milky Way sits inside a bubble where matter is spread more thinly than the cosmological principle allows. The light from those galaxies still reaches us crossing the dark, but the intervals between them are wider, the clusters smaller, the web stretched into a lacework that should not hold together at this scale. The deficit is not confined to a narrow shell. It begins within tens of millions of light-years and persists outward, a thinning that deepens gradually as the surveys push to greater distances. Imagine standing in a forest where the trees grow steadily farther apart as you walk, until finally, at the forest's edge, the spacing returns to normal. That edge lies at a distance of about 500 megaparsecs. There, the density of galaxies in near-infrared light finally reaches the cosmic mean. Beyond that threshold, the universe looks the way the standard model predicts. The galaxies are there, in the numbers expected, arranged in clusters and superclusters and voids of their own. But between here and there, across a volume 500 million light-years deep in every direction, the count comes up short. The overall diameter of the underdensity clusters around 600 megaparsecs, roughly 2 billion light-years from edge to edge. This makes it one of the largest known cosmic underdensities ever mapped. Other enormous voids exist, the Boots void among them, but few rival the scale of the structure we call home. The local group, the small cluster of galaxies that includes the Milky Way and Andromeda, lies inside it. The wider Laniakea supercluster, the vast river of galaxies to which our local group belongs, a supercluster spanning 500 million light-years and containing 100,000 large galaxies, lies inside it. All the familiar landmarks of the local universe fit comfortably within the bubble's walls. We do not sit at the edge of the bubble, looking in or out. We sit near the center. That placement is not arbitrary. For the void to be consistent with the smallness of the cosmic microwave background dipole, the Milky Way must be located near the center of the underdensity. If we were far from the center, the gravitational pull from the denser regions on one side would produce a large peculiar velocity, a motion through space that would show up as a lopsided temperature pattern in the microwave background. A dipole so pronounced it would have been impossible to miss. The dipole we measure is small. The local group moves at 627 kilometers per second relative to the cosmic microwave background, a velocity consistent with our location inside a sparser-than-average region, but not with a position far from its heart. The data place us, gently but firmly, near the middle of the whole. Imagine a sphere 600 megaparsecs wide, its surface touching the edge, where galaxy density returns to normal. Now imagine it drawn on a map of the universe, centered on the Milky Way. Every survey that has counted galaxies within that sphere, using near-infrared light or optical light or radio waves or X-rays, has found the same deficit. The pattern shows up no matter which kind of light we use to look. Radio galaxy counts reveal it. X-ray surveys of galaxy clusters, which trace the hot gas that fills the space between galaxies, reveal it. Optical and infrared catalogs, each compiled by different teams using different instruments, reveal it. The galaxies are simply not there, at roughly half the density the standard model expects on this scale. The void is not an artifact of one telescope, or one team, or one wavelength. It is written into the large-scale structure of space itself. The standard model predicted variations of only about 3% from one place to another. The measured density contrast is 0.46, that is not 3%, that is 46%, a deficit nearly half again as deep as the cosmic mean. The universe at this scale should be smoothed to within 3% of perfection, and instead we find ourselves inside a hole that holds only about 54% of the expected density. The gap between expectation and reality is roughly 15 times wider than the model allows, a feature so pronounced that it challenges the very assumption of smoothness on which the standard model rests. No one predicted a structure this large, this deep, this close. The dimensions of the void do more than challenge the cosmological principle. They offer a bridge to the other great puzzle of modern cosmology, the one that has split the universe's two clocks. If we live inside a region of below-average density, the galaxies on the void's edge are gravitationally pulled outward, as the rest of the universe pulls them away. Matter flows from the sparse interior toward the denser surroundings, a slow tide that has been running for billions of years. The light from those galaxies reaches us more redshifted than it would be if space were uniformly filled, their recession velocities inflated by the outward flow. A local measurement of how fast the universe is expanding, taken from inside the void, will be inflated above the true cosmic mean value. The size of the hole, and the speed at which the universe seems to be expanding around us, point at the same answer. The two anomalies are not independent. They are two faces of the same underlying picture. The void is not a gravitational well. It does not trap light or bend spacetime into a pit. The metaphor of being trapped inside a hole is poetic, not literal. A void is simply an underdense region, a place where the cosmic web is stretched more thinly, where the filaments are farther apart and the clusters fewer. But the metaphor captures something true about our situation. We are embedded in a structure that should not exist at this scale, a bubble of relative emptiness 2 billion light-years wide, and that bubble may be rewriting the numbers we use to describe the universe's expansion. The void does not hold us in place. It tilts the frame through which we measure everything beyond. The dimensions are now known. The density contrast is measured. The distance to the edge, the placement of the Milky Way near the center, the agreement across independent surveys in every band of light, the persistence of the deficit from 40 megaparsecs out to 500, all point to the same picture. We are not looking at noise. We are looking at a feature of the universe on the largest scales we can map, a feature the standard model says should not be there, and we are looking at it from the inside. The forest thins around us, and the thinning has a shape, a depth, a center. The void is real. The question is what it means. We measure the universe with two clocks, and the clocks refuse to agree. The Hubble constant is one of the most fundamental numbers in all of cosmology. It tells us how fast the universe is expanding today, in units of kilometers per second per megaparsec, a measure of how quickly galaxies recede from one another as space itself stretches. If you know the Hubble constant, you can run the film of cosmic history backward and forward. You can date the Big Bang. You can predict the future geometry of everything. For most of a century, the measurements converged, slowly, toward a single number. Then they stopped converging. They split. The first clock ticks in the afterglow of the Big Bang itself. The Planck satellite spent years staring at the cosmic microwave background. The faint wash of radiation released when the universe was only 380,000 years old. Planck measured the tiny fluctuations in that light, hot spots and cold spots imprinted across the whole sky, each one a seed from which galaxies and clusters would later grow. The fluctuations are exquisitely small, variations of only 1 part in 100,000. Planck fed those fluctuations into the standard model of cosmology and let the equations run forward across 13.8 billion years of expansion. The model predicted what the expansion rate should be today. The answer it gave was 67.4 kilometers per second per megaparsec, with an uncertainty of only half a unit either way. The second clock ticks in the light of stars that pulse. The SH0ES collaboration, led by Adam Rees, built what astronomers call a distance ladder, a series of overlapping measurements that reach from nearby stars all the way out to galaxies billions of light-years away. The first rung is anchored to Cepheid variable stars, massive young stars, whose brightness rises and falls in a rhythm that depends on their intrinsic luminosity. Measure the period of the pulse, and you know how bright the star truly is. Compare that to how bright it appears, and you know how far away it sits. Cepheids are bright enough to be seen in neighboring galaxies, and so they serve as calibrators for the next rung. Type Ia supernovae, exploding white dwarf stars that blaze with nearly identical peak luminosities, no matter where or when they detonate. Supernovae can be seen across billions of light-years, far enough that the expansion of the universe measurably stretches their light. By comparing distances to supernovae with their redshifts, the SH0ES team measured the expansion rate directly, without feeding anything through a cosmological model. Their result, refined over years and tightened with data from the Hubble Space Telescope and later the James Webb Space Telescope, came in at 73.04 kilometers per second per megaparsec. A later calibration pushed the value slightly higher to 73.17. The two numbers disagree at a level that, in any other branch of physics, would be called a discovery. The gap between them is roughly 5 to 6 standard deviations, well above the threshold that physicists conventionally treat as proof that something real is happening. One clock says the universe is expanding at 67.4. The other says 73. Both measurements are precise. Both teams have checked and rechecked their work. The tension has not gone away. A third method has entered the conversation. The dark energy spectroscopic instrument maps the large-scale structure of the universe by measuring the positions of millions of galaxies and quasars. Embedded in that structure is a faint pattern called baryon acoustic oscillations, ripples in the distribution of matter left over from sound waves that traveled through the hot plasma of the early universe. The ripples provide a standard ruler, a known length scale imprinted in the cosmic web. By measuring how that ruler appears at different distances, DESI can infer the expansion history of the universe. When its first data release was combined with constraints from Big Bang nucleosynthesis, the result for the Hubble constant came out to around 68.5 kilometers per second per megaparsec. The second data release with improved precision did not move the needle. DESI agrees with Planck. It does not agree with SH0ES. The James Webb Space Telescope, with its sharper near-infrared vision, was expected by some to resolve the tension by revealing a subtle systematic error in the Cepheid measurements. Crowding was a concern. In dense star fields, the light of multiple stars can blend together, making a Cepheid appear brighter than it truly is. But when the SH0ES team recalibrated their Cepheid distances using Webb's data, they found no such bias. The high value held. An alternative distance ladder, built using the tip of the red giant branch, the brightest red giants in old stellar populations, has yielded intermediate values, around 69 to 72, closer to Planck, but not coincident with it. The tension remains. No one expected this. The standard model is built on the assumption that the universe, on the largest scales, is smooth and uniform. If that assumption is correct, then every method of measuring the Hubble constant should converge on the same number. The fact that two precise, independent methods disagree suggests that something about our picture is incomplete. Either the model itself is missing some new physics, or one of the measurements is not seeing what we think it is seeing. This is where the void re-enters the story. If we are inside a region of below-average density, then the galaxies around the edges of that region are not moving the way galaxies in an average part of the universe would move. The rest of the universe, denser and more massive, pulls outward on them. They fall away from us, not only because space is expanding everywhere, but because they are being gravitationally tugged toward the denser surroundings. Their motion has two components: the smooth Hubble flow that carries everything apart, and an additional outward drift driven by the density contrast. When we measure their redshift, the stretching of their light, we see both components blended together. We cannot separate them without already knowing the density structure around us. And so the redshift looks higher than it should. The galaxies appear to be receding faster than the cosmic mean expansion would predict. Our measurement of the Hubble constant, taken from inside the void, gets pulled up. The effect is not small. If the void has a density contrast of roughly 46%, meaning it holds only about half as much matter as the average region of the universe, and if we sit near its center, then the local measurement of the expansion rate should come out approximately 11% higher than the true cosmic mean value. 11% of 67.4 is about 7 units. Add them together, and you get 74.7, very close to what SH0ES actually measures. The size of the hole, and the speed at which the universe seems to be expanding around us point at the same answer. This is not proof. It is a coincidence, and coincidences in cosmology can mislead. But it is a precise coincidence, one that arises naturally from the same mass distribution that multiple teams have now measured in multiple ways. The void does not require any new physics. It does not ask us to modify the laws of gravity or invent a new particle. It asks only that we take seriously the possibility that our neighborhood is not average, that the cosmological principle breaks down on scales smaller than the whole observable universe, and that we happen to live in one of the places where it breaks down. The alternative is to accept that the void is real but irrelevant, that it does not bias the distance ladder, and that the Hubble tension points instead towards something deeper. Some researchers, particularly those who built the SH0ES distance ladder, argue exactly this. They have tested whether local structure could inflate their result, and concluded that it does not, that the high value of 73 is robust. In this view, the void is an interesting feature of our cosmic neighborhood, but it is not the answer to the tension. The tension demands something more fundamental. The two explanations are not mutually exclusive. The void could be real and significant, and there could also be new physics. The universe is under no obligation to offer us only one surprise at a time. What we know for certain is that the two clocks disagree. Planck's measurement comes from the early universe, from a time when the cosmos was smooth and simple. The SH0ES measurement comes from the local universe, from a web of stars and supernovae within a few billion light-years of here. DESI's measurement comes from the large-scale structure of matter, from the faint echo of sound waves imprinted when the universe was 1,000 times smaller. All three methods are precise, all three are independent, and they do not agree. The void offers a way to reconcile them without abandoning the standard model. If the local universe is genuinely underdense, then the early universe measurement and the large-scale structure measurement are both correct. They are measuring the true cosmic mean, and the local measurement is also correct, but it is measuring something slightly different. The expansion rate, as it appears from inside a sparser-than-average bubble. The tension is not a crisis, it is a symptom of where we are. But that explanation only works if the void is as large and as deep as the measurements suggest, and if we sit close enough to its center, that the outflow is symmetric. The cosmic microwave background shows a dipole, a pattern in which one half of the sky is slightly hotter, and the other half slightly cooler, interpreted as the Doppler shift, caused by our motion through space, at 627 kilometers per second. If we were far from the center of a large void, the asymmetry would be larger. The fact that the dipole is as small as it is, suggests that if the void is real, we are indeed near the middle of it. That is a remarkable coincidence on its own. The standard model says voids this large should be rare. It says we should not be inside one. And it says that if we are, we probably should not be sitting near the middle. One team, working through the numbers in detail, concluded that the combination of the void and the Hubble tension together represents a departure from the standard model at more than 7 standard deviations. They proposed that an alternative theory of gravity could produce both the void and the tension naturally. This view is not the consensus, and most cosmologists remain committed to the standard model, but the fact that it has been proposed at all is a measure of how seriously the tension is being taken. The question is still open. No single instrument has yet delivered a verdict. DESI is still mapping the large-scale structure of the universe, refining the baryon acoustic oscillation ruler with every new data release. The James Webb Space Telescope is still recalibrating the distance ladder, reaching farther and seeing more clearly than any telescope before it. Euclid, launched in the summer of 2023, is surveying 15,000 square degrees of sky, measuring the shapes of billions of galaxies to map the distribution of dark matter. Each new result tightens the constraints, narrows the range of possibilities, brings the picture a little closer to clarity. And beneath it all, the two clocks keep ticking, each one precise, each one confident, each one telling a different time. In December of 2020, a team at the University of Bonn published a paper that tried to do something simple: put numbers to the bridge between the hole and the clock. Moritz Hasselbauer, Indranil Banik and Pavel Krupa took the measured size and depth of the void, the numbers Keenan, Barger and Cowie had drawn from the galaxy counts, and asked what that structure would do to an observer sitting near its center. They assumed mass conservation, the rule that matter cannot simply vanish. If the region around us holds only about half as many galaxies as the cosmic average, then the denser universe beyond must pull outward on everything near the boundary. Galaxies at the edge of the void would appear to recede faster than they should. Their light would be stretched more than the true cosmic expansion alone would predict. A measurement of the Hubble constant taken from inside the void would come out higher than the real value. They calculated the size of that error. An observer at the center of a void with a density contrast of 0.46, the value measured from the 2-micron surveys, should measure a local Hubble constant roughly 11% higher than the true cosmic mean. The Planck satellite, looking back at the cosmic microwave background and running the numbers forward through the standard model, had found 67.4 kilometers per second per megaparsec. Raise that by 11%, and the number becomes 74.7. The SH0ES collaboration, measuring Cepheid variable stars and Type E supernovae in the local universe, had reported 73. The size of the hole and the speed at which the universe seems to be expanding around us point at the same answer. No one expected the two numbers to line up so closely. The void had been mapped as a curiosity, a sparse bubble in the local neighborhood. The Hubble tension had been treated as a puzzle about instruments, about systematics, about the distance ladder or the cosmic microwave background analysis. Hasselbauer and his colleagues were proposing that the two puzzles were not separate. The void was not merely an interesting backdrop, it was the reason the clocks disagreed. To test whether the void itself was plausible within the standard model, they turned to the Millennium XXL simulation, one of the largest cosmological simulations ever run. The simulation modeled a cube of space 3 billion light-years on a side, filled with more than 6,700 particles cubed, each representing a clump of dark matter. The simulation followed the rules of lambda CDM cosmology, letting gravity pull the matter into filaments and clusters and voids over billions of years of cosmic time. The team sampled 1 million random vantage points within that simulated universe and measured the density around each one, averaging over spheres 300 megaparsecs across. They wanted to know how much variation the standard model naturally produces on that scale. The answer came back: about 3.2% in real space. When they corrected for the way peculiar velocities distort redshift measurements, the way galaxies moving toward or away from us stretch or compress the apparent distance scale, the number rose slightly to 4.8%. The universe, according to lambda CDM, should look almost perfectly smooth when averaged over a sphere 600 megaparsecs wide. Variations of only a few percent from one place to another, the density might dip here, rise there, but never by much. The cosmic microwave background, released 380,000 years after the Big Bang, showed temperature variations of only 1 part in 100,000. Gravity has had nearly 14 billion years to amplify those tiny seeds, but the power spectrum that governs their growth is scale invariant. On the largest scales, the universe should still be almost featureless. The observed density contrast of the void, 0.46, plus or minus 0.06, is not a few percent. It is nearly 50%. For every 2 galaxies the average region of the universe contains, our local neighborhood holds only about 1. Hasselbauer and his colleagues compared that measurement to the distribution of density contrasts in the Millennium XXL simulation. They found that the KBC void, treated on its own, sits in 6 standard deviations of tension with lambda CDM cosmology. 6 sigma. A result that far from the expected distribution in a simulation sampling 1 million vantage points should not happen by chance. Then they combined the void measurement with the Hubble tension. The disagreement between Planck and SH0ES, evaluated using the data available at the time, stood at 5.3 standard deviations. The two anomalies are not independent. If the void is real, it predicts a higher local Hubble constant. If the local Hubble constant is genuinely high, it implies we sit inside an underdense region. The team ran a joint analysis, treating both measurements as constraints on the same underlying cosmology. The combined tension came out to more than 7 standard deviations. Taken together, the void and the disagreement over the expansion rate are more than 7 sigma away from what the standard model can produce on its own. No one predicted that the numbers would converge this way. The cosmological principle, the assumption that every large neighborhood looks like every other, had stood for a century. The standard model had passed test after test. The cosmic microwave background, the abundances of light elements, the growth of structure, the acceleration of the expansion, all of it fit. And now 2 independent lines of evidence, one counting galaxies in every direction, the other measuring the stretching of space itself, were pointing at the same conclusion, that our corner of the universe is not ordinary. The same team proposed one possible resolution. They suggested that Milgromian dynamics, an alternative theory of gravity called MOND, developed in the 1980s to explain the rotation curves of galaxies without invoking dark matter, supplemented with sterile neutrinos of mass 11 electron volts, could reconcile the observations. In their view, the standard model's assumption of cold dark matter might be the wrong framework entirely. MOND changes the way gravity behaves at very low accelerations, and on the scales of galaxies and voids, those changes accumulate. This view is not the consensus, and most cosmologists remain committed to lambda CDM. The proposal remains controversial, debated in the literature but not widely adopted. Follow-up work has continued to refine the void hypothesis. In 2024, Sergej Mazurenko, Banik, Krupa, and Hasselbauer published an analysis of the bulk flow of galaxies within 250 megaparsecs, testing whether the void's gravitational signature shows up in the pattern of peculiar velocities. In 2025, Mazurenko, Banik, and Krupa examined predictions for baryon acoustic oscillations, the faint ripples in the galaxy distribution left over from sound waves in the early universe, and how those predictions change if the observer sits inside a large underdensity. The numbers are still being tested. The void has not been ruled out, but neither has it been confirmed beyond all doubt. The bridge between the void and the Hubble tension rests on a simple idea, that if we are inside a sparser-than-average bubble, the universe around us does not expand at the average rate. The outward flow of galaxies at the void's edge makes the local expansion look faster than it truly is. The measurement we take from our position, using stars and supernovae as distance markers, captures that local flow, not the cosmic mean. The measurement Planck takes, looking back at the microwave background and averaging over the entire observable universe, captures the mean. Both measurements are correct. They are simply measuring different things. The possibility that we sit near the center of a void 2 billion light-years wide, in a universe that should not produce such a structure, has not gone away. The galaxy counts, in infrared and optical and radio and X-ray light, continue to come up short. The Hubble constant, measured locally, continues to come out high, and the simulation that was meant to show how the universe grows from smooth beginnings into the lumpy web we see today, cannot easily produce a hole this deep, this wide, and this close to home. The numbers point at the same answer. Whether that answer is the void or a revision to the standard model or both, remains an open question. The instruments are still counting. The light is still traveling. And the bubble we call home, quieter than the universe at large, waits to be mapped in full. The standard model of cosmology rests on a single, elegant assumption, that the universe, viewed from far enough away, looks the same in every direction and from every vantage point. On the largest scales, one neighborhood should resemble another. The cosmic microwave background, released 380,000 years after the beginning, bears this out. Its temperature varies by only 1 part in 100,000 from place to place across the sky. The early universe was extraordinarily smooth. Gravity has had nearly 14 billion years to amplify those tiny ripples into the structures we see today. Galaxies clustered along filaments, separated by voids where almost nothing lives. But the power spectrum that describes those initial fluctuations, measured with exquisite precision by the Planck satellite, carries a strict prediction about how lumpy the universe can become. The shape of that spectrum follows what cosmologists call the Harrison-Zeldovich form, a scale-invariant pattern imprinted in the first moments. Run forward through billions of years of gravitational collapse. That spectrum predicts that on a scale of 300 megaparsecs, the universe today should be smoothed to within about 3%. Density should vary from one region to another by no more than that small fraction. No one expected what the galaxy counts revealed. When astronomers measured the density of galaxies in our local neighborhood, out to distances of a few hundred megaparsecs, and compared it to the density further away, the mismatch was not 3%. It was closer to 50%. For every 2 galaxies the standard model expects, our region holds only about 1. The observed density contrast came out to roughly 0.46. The universe at this scale should be smoothed to within 3% of perfection. Instead, we find ourselves inside a hole that is almost half empty. The number is not an artifact of a single survey. The same underdensity appears in near-infrared light, traced by the 2-micron all-sky survey and its successors. It appears in optical galaxy counts from the Sloan Digital Sky Survey. It appears in radio surveys that map distant galaxies by their emission at centimeter wavelengths. It appears in X-ray catalogs of galaxy clusters, massive structures whose hot gas glows in high-energy light. The Boehringer team, analyzing cluster surveys, found a 15 to 30% matter deficit within 100 megaparsecs of the Milky Way. The pattern shows up no matter which kind of light we use to look. The galaxies are simply not there. The most natural explanation, if one wishes to preserve the standard model, is measurement error. Perhaps the photometry is biased. Perhaps the redshifts are contaminated. Perhaps dust extinction, or galaxy evolution, or selection effects have conspired to make the local universe look emptier than it is. But the underdensity is detected at multiple wavelengths by independent teams, using different methods and different catalogs. A coordinated multi-wavelength systematic error, affecting infrared and optical and radio and X-ray surveys in exactly the same way, is very unlikely. The simplest reading of the data is that the deficit is real. If the deficit is real, it poses a problem for the standard model that is not merely observational but structural. The power spectrum measured by Planck, with its normalization parameter equal to 0.811, predicts root mean square density variations of only about 3.2% on a 300 megaparsec scale. The observed value is roughly 15 times deeper. The hole we live in is not a modest fluctuation around the cosmic mean. It is an outlier that the model in its current form should produce only vanishingly rarely. Hasselbauer, Banach, and Krupa, working at the University of Bonn, tested this claim directly in 2020. They took the Millennium XXL simulation, a standard cosmological calculation that follows the evolution of more than 300 billion dark matter particles inside a box 3000 megaparsecs on a side. They sampled 1 million random vantage points within that simulated universe, and measured, from each one, the density contrast on a 300 megaparsec scale. The distribution they obtained represents what the standard model, with all its parameters fixed by Planck, predicts an observer should see. The root mean square fluctuation came out to 3.2% in real space, and 4.8% after correcting for the way peculiar velocities distort redshift measurements. The observed value, 0.46, lies more than 6 standard deviations away from that distribution. If the standard model is correct, the probability of finding ourselves inside a void this deep is less than 1 in a billion. No one predicted that the void and the Hubble tension would be two faces of the same underlying picture. But mass conservation provides the bridge. If our local region is genuinely underdense, the gravitational pull from the denser surroundings beyond drags galaxies outward. The void does not sit still. Its edges are falling away from us, pulled by the greater mass of the cosmic web beyond. A galaxy sitting on the boundary between the sparse interior and the denser exterior receives an outward tug. Its recession velocity, measured by the redshift of its light, comes out higher than it would if the universe were perfectly smooth. The locally measured Hubble constant must come out higher than the global cosmic value inferred from the early universe. The two anomalies are not independent. They are the same structure, seen from two different angles. Hasselbauer and his colleagues worked through the mathematics of this outflow. They assumed an observer at the center of a spherical underdensity, with a density contrast of 0.46, and they applied the equations of mass conservation in an expanding universe. The result: such an observer should measure a local Hubble constant approximately 11% higher than the true cosmic mean. If the Planck satellite's value of 67.4 km per second per megaparsec is the true cosmic mean, an observer inside the void should measure roughly 74.7. The SH0ES collaboration, using Cepheid variable stars and Type Ia supernovae as distance markers, measures 73. The size of the hole and the speed at which the universe seems to be expanding around us point at the same answer. The standard model does not forbid voids, it predicts them. The cosmic web is a tapestry of clusters and filaments and empty spaces, but it predicts voids of a certain size and depth, consistent with the smoothness of the early universe and the growth of structure over time. The KBC void, if the measurements hold, exceeds those predictions by a wide margin. It is not that the void should not exist at all. It is that a void this large and this deep, with us sitting near its center, should not happen in a universe governed by the lambda CDM model, with the parameters Planck measured. The two pictures do not fit together. The tension is not resolved by appealing to cosmic variance. Cosmic variance describes the uncertainty that arises because we observe only one patch of the universe. If we could see 1,000 independent regions, each 300 megaparsecs wide, we would expect them to vary around the mean by a few percent. But the variance predicted by the standard model is itself only a few percent. A fluctuation of 50% lies far beyond what cosmic variance allows. The void is not a typical fluctuation, it is an extreme event, one that the model assigns a probability so low that invoking chance becomes uncomfortable. The alternative is that something in the standard model needs adjustment. Perhaps the initial power spectrum was not perfectly scale invariant. Perhaps the growth of structure proceeded differently than the equations predict. Perhaps dark energy has evolved over time in a way that allowed larger voids to form. Or perhaps the cosmological principle itself, the assumption that the universe looks the same from every vantage point, is only approximately true, and we live in a region where that approximation breaks down. Each of these possibilities opens a door to new physics. None has yet been proven. The void and the Hubble tension together form a picture that is harder to dismiss than either anomaly alone. Taken separately, each could be explained away, but taken together, the two anomalies support each other. The void predicts a local expansion rate higher than the global mean. The distance ladder measures exactly that. The team at Bonn concluded that, taken together, the void and the disagreement over the expansion rate are more than 7 standard deviations away from what the standard model can produce on its own. If that assessment holds, it is not a minor discrepancy, it is a signal that the framework needs revision. And yet the whole is not the only answer being weighed. The universe's 2 clocks refuse to agree, and some of the teams who built those clocks have looked at the same underdensity and concluded that it is real, but not enough. In 2019, Kenworthy, Skolnick, and Rees, architects of the supernova distance ladder, argued that local large-scale structure, including the void we appear to inhabit, does not significantly bias the measurement of the expansion rate. In their view, the whole is there, mapped across wavelengths and confirmed by independent counts, but it does not resolve the tension. The disagreement between the early universe's prediction and the local universe's measurement they propose demands something deeper, new fundamental physics, a revision to the model itself, not merely a correction for where we happen to stand. The void may be extraordinary, but the clocks are telling us about something more fundamental than geography. Meanwhile, the void hypothesis itself has been retested. In 2025, Mazurenko, Banach, and Krupa returned to the question, with direct distance tracers drawn from the COSMICFLOWS4 Tully-Fisher catalog. Measurements of galaxy distances that rely not on redshift alone, but on the intrinsic brightness of rotating spiral galaxies, a ruler independent of the expansion itself. The data they analyzed prefer a void approximately 10% the size of the original model proposed in 2020. The underdensity remains, but narrower, shallower, less dramatic than the early estimates suggested. The case has not been eliminated, but it has been narrowed, its edges drawn inward by more precise counts. The whole is still there, but smaller, and the question of whether it can account for the tension between the two measurements of expansion has grown more uncertain. Beyond the void, other ideas are being explored. Some propose that dark energy was not always the quiet constant we have assumed, that in the earliest moments after recombination it was active, a force called early dark energy that briefly accelerated the universe's expansion before fading into the background. Others suggest additional relativistic species, particles moving near the speed of light that we have not yet detected, their presence felt only in the way they subtly alter the expansion history, the way they leave faint imprints in the distribution of matter and the temperature of the cosmic microwave background. Still others propose interactions between dark matter and dark energy, forces that couple the invisible skeleton of the cosmos to the invisible pressure pushing it apart, a conversation between the two dominant components of the universe that the standard model does not currently allow. And some reach further still, proposing modifications to gravity itself, adjustments to the equations that have held since Einstein, tweaks that would alter how structure grows and how light bends across the largest scales. None of these ideas has yet reached the threshold of confirmation. They are proposals, sketches, frameworks being tested against data that continues to arrive. Each idea carries its own predictions, its own signatures, and each must wait for instruments sensitive enough to distinguish one possibility from another. And the data continues to arrive. The dark energy spectroscopic instrument has been measuring the imprint of baryon acoustic oscillations, the faint ripples left over from the early universe, now frozen into the distribution of galaxies, a standard ruler stretching across billions of light-years. Its first data release, published in 2024, hinted at something unexpected, that dark energy may be evolving over cosmic time, that the pressure driving the universe's acceleration is not constant, but changing, a function that shifts as the universe ages. The second data release, in 2025, sharpened the measurement, and the hint persisted. The data are suggestive, not yet definitive, but if the hint holds, it would itself be a major modification to the standard model, independent of the void question. The universe's expansion would not be driven by a single unchanging force, but by something that adapts, that responds to the passage of time, in ways we do not yet understand. Euclid, the European Space Agency's satellite launched in July 2023, is conducting a survey across 15,000 square degrees of sky, measuring the way gravity bends light and the way galaxies cluster across billions of years. It is designed to measure weak lensing and galaxy clustering with percent-level precision, a map of the universe's dark matter scaffolding so detailed that it will reveal whether the Standard Model's predictions hold or fracture. Its primary cosmological results are expected from 2026 onward. The telescope is already operating, already gathering light, the counts accumulating in silence. In Chile, the Vera C. Rubin Observatory waits with its primary mirror spanning 8.4 meters, ready to begin the legacy survey of space and time. Over the next decade, it will image the entire visible sky, night after night, building a map of the local galaxy density with unprecedented depth, and a supernova distance ladder recalibrated by sheer volume. The survey will dramatically improve our understanding of the void's shape, its edges, the gradient of density as you move outward from our position near the center. It will count galaxies in every direction, and the counts will either confirm the underdensity or dissolve it into the noise of measurement. Further out in time, the Nancy Grace Roman Space Telescope, planned for launch around 2027, will join the effort, its instruments tuned to measure dark energy's evolution and the cosmic web structure at the scales relevant to the void question. It will map the distribution of galaxies and the distances to supernovae, with a field of view 100 times larger than the Hubble Space Telescope's, a census of the universe's expansion history across 10 billion years. And beyond that, around 2035, LISA, the Laser Interferometer Space Antenna, will listen for gravitational waves from merging black holes across cosmic time. A different kind of ruler, a different way of measuring how the universe has grown. The question remains open: whether we are genuinely inside an extraordinary structure, a sparser-than-average bubble 2 billion light-years wide that the Standard Model says should not exist, or whether the cosmology itself needs revision, or both. No single instrument has yet delivered a verdict. The void may be real and still not resolve the tension. The tension may demand new physics, and the void may still be there, a coincidence of location and cosmic history, two separate puzzles that happen to occupy the same neighborhood of the universe. The two clocks may disagree for reasons that have nothing to do with where we stand, and the underdensity may be an unrelated feature, a sparser neighborhood in a universe that permits such neighborhoods more easily than the current model predicts. You are left for now with the image: a cosmic neighborhood quieter than the universe at large, fewer galaxies in every direction, out to a distance of roughly 500 megaparsecs, and then, beyond that edge, the counts rising to what the Standard Model expects. A bubble, not a trap, not a well, but a region where matter is simply less common, where the web of filaments and clusters thins, and the voids between them widen. The Milky Way, the local group, the whole of Laniakea, sitting near the center of this sparser zone, not by design but by the accident of initial conditions, the fluctuations imprinted in the first moments after the Big Bang, grown over 13.8 billion years into the structure we now map. Euclid is still operating. The dark energy spectroscopic instrument is still counting. The James Webb Space Telescope is still measuring distances to Cepheid variables. The numbers are still coming in. The frontier is open, the question unresolved, the instrument still pointing outward into the dark, waiting for the universe to tell us whether the whole is ordinary or extraordinary, whether the clocks disagree because of where we stand, or because the model itself is incomplete. We turn now to the moment when the numbers stopped making sense. For a century, cosmology has rested on one quiet assumption: the universe, viewed on large enough scales, looks the same in every direction and from every location. Homogeneous and isotropic. the cosmological principle. It is the foundation of the lambda CDM standard model, the framework that describes the origin, evolution, and fate of everything we can see. Under this principle, no place is special, no observer sits at the center. Every cosmic neighborhood, given enough volume, resembles every other. The cosmic microwave background, released 380,000 years after the Big Bang, shows temperature variations of only 1 part in 100,000. The early universe was extraordinarily smooth. From those tiny seed fluctuations, gravity built the cosmic web over billions of years, clusters, filaments, and voids. But the largest voids should not exceed the size predicted by the power spectrum of those initial ripples. The standard model predicts that on a scale of 300 megaparsecs, the universe should look almost perfectly smooth. Variations of only about 3% from one place to another. Then astronomers started counting galaxies. To map the matter distribution of the local universe, they count galaxies as traces of the underlying mass. Near-infrared light, around 2.2 micrometers, traces stellar mass more directly than optical light. Dust extinction is minimal. The 2-micron all-sky survey, published in 2006, imaged the whole sky in this wavelength. The 2M++ catalog combines that infrared photometry with spectroscopic redshifts from 3 major surveys, covering roughly 90% of the sky. The counts kept coming up short. Hints had been accumulating for 30 years. In 1990, optical galaxy counts suggested a deficit. Through the 1990s and 2000s, the hint sharpened. In 2003, a team analyzing 2MASS data found a 30% deficit of galaxies in the southern galactic cap and 18% in the northern galactic cap, on a scale of about 150 megaparsecs. They named the feature the local hole. In 2014, extending the analysis with redshifts from 3 major surveys, another team concluded that the local group inhabits a hole in the large-scale structure of the universe, with redshift distributions consistently underdense by 4 to 40%, deepest in the southern galactic cap. In 2022, a follow-up extended the analysis to 90% of the sky, finding a 21 to 22% underdensity, a deviation from lambda CDM expectations at nearly 3 standard deviations. The same underdensity showed up no matter which kind of light was used to look: radio, infrared, X-ray, optical. The galaxies were simply not there. In September 2013, Ryan Keenan, Amy Barger, and Lennox Cowie published a paper in the Astrophysical Journal that gave the structure its modern name, the KBC void. They measured the K-band galaxy luminosity density as a function of redshift over the range from roughly 50 to 800 megaparsecs, using the UKIDSS Large Area Survey, supplemented by the 2M++ catalog. They found that the K-band luminosity density beyond a certain distance is approximately 1.5 times higher than the value measured locally. Beyond a certain distance, galaxies become roughly 50% more common than they are around us. The shape of the luminosity function remains constant with redshift, meaning the rising density is genuine and not an artifact of galaxy evolution. The authors noted that a hole of roughly this size and depth would by itself be enough to make the universe's 2 clocks disagree. Adopting a deeper subsample of the 2M++ catalog, the density contrast between 40 megaparsecs and 300 megaparsecs is measured at 0.46, plus or minus 0.06. For every 2 galaxies the average region of the universe contains, our local neighborhood holds only about 1. The K-band luminosity density reaches the cosmic mean at roughly 500 megaparsecs from us. Beyond that distance, the density of galaxies is what the standard model predicts. Estimates of the void's overall diameter cluster around 600 megaparsecs, roughly 2 billion light-years, making it one of the largest known cosmic underdensities. The local group, the Milky Way, and the wider Laniakea supercluster all lie inside the KBC void. For the void to be consistent with the smallness of the cosmic microwave background dipole, the Milky Way must sit near the center of the underdensity. The local group moves at 627 kilometers per second relative to the cosmic microwave background, a peculiar velocity consistent with our location inside a sparser than average region. No one expected this. The universe at this scale should be smoothed to within 3% of perfection, and instead we find ourselves inside a hole that is almost half empty. The structure of the universe today grew from initial density fluctuations imprinted at the time of the cosmic microwave background. The shape of those fluctuations is well measured. It follows the Harrison-Zeldovich scale invariant power spectrum, with normalization from Planck. That power spectrum, run forward to today, predicts root mean square density variations of only about 3.2% on a 300 megaparsec scale. The observed value is roughly 15 times deeper, and the hole may explain something even stranger. The Hubble constant measures how fast the universe is expanding today. It is one of the most fundamental numbers in cosmology. Two precise methods of measuring it disagree at a level the cosmology community calls the Hubble tension. The first method uses the cosmic microwave background. The Planck satellite measured tiny fluctuations in that ancient light, then ran them forward through the lambda CDM model. The result, 67.4 kilometers per second per megaparsec, plus or minus half a unit. The second method uses a distance ladder. The SH0ES collaboration, led by Adam Rees, measured the expansion rate directly using Cepheid variable stars and type Ia supernovae. Their result has tightened over the years, 73.04, and in the latest work, 73.17. The two numbers disagree at a level that, in any other branch of physics, would be called a discovery. The disagreement currently sits at roughly 5 to 6 standard deviations of statistical significance, well above the threshold physicists conventionally treat as proof. The dark energy spectroscopic instrument provides an independent measurement via baryon acoustic oscillations. Its result yields a value around 68.5, consistent with Planck and in tension with SH0ES. The James Webb Space Telescope has been used to recalibrate the SH0ES Cepheid distance ladder. It confirmed the local high value rather than collapsing it. An alternative ladder using the tip of the red giant branch finds intermediate values, closer to but not coincident with the Planck value. No one predicted the void would be there to resolve it. If we live inside a region of below average density, galaxies on the void's edge are gravitationally pulled outward. The rest of the universe pulls them away. Their redshift looks too high. If we are inside a void, the galaxies around its edges fall outward. The light they send us looks more redshifted than it should. Our measurement of how fast the universe is expanding gets pulled up. In December 2020, Moritz Hasselbauer, Indranil Banik, and Pavel Krupa published a paper in Monthly Notices of the Royal Astronomical Society. They derived, under the assumption of mass conservation, that an observer at the center of a void with a density contrast of 0.46 should measure a local Hubble constant approximately 11% higher than the true cosmic mean value. This would raise the Planck-derived value of 67.4 to roughly 74.7, very close to what SH0ES actually measures. The size of the hole, and the speed at which the universe seems to be expanding around us, point at the same answer. They compared the observed KBC density contrast to predictions from the Millennium XXL cosmological simulation, a standard lambda CDMN body simulation. Sampling 1 million vantage points within the simulation, they computed the root mean square density fluctuation expected on a 300 megaparsec scale, 3.2% in real space, 4.8% after correction for redshift space distortion. Comparing the observed density contrast against the simulated distribution, they found the KBC void to be in 6 standard deviations of tension with lambda CDM cosmology when treated alone. Combined with the Hubble tension, the team concluded that, taken together, the void and the disagreement over the expansion rate are more than 7 standard deviations away from what the standard model can produce on its own. Mass conservation provides the bridge. If the local region is genuinely underdense, the gravitational pull from the denser surroundings drags galaxies outward. The locally measured Hubble constant must come out higher than the global cosmic value. The two anomalies are not independent. They are two faces of the same underlying picture. The most natural lambda CDM compatible explanation for the KBC measurement, if one rejects the void as physical, is measurement error. But the underdensity is detected at multiple wavelengths by independent teams using different methods. A coordinated multi-wavelength systematic error is very unlikely. The verdict is not yet in. Some researchers argue from the SH0ES side that local large-scale structure does not significantly bias the measurement of the Hubble constant. In this view, the void is real but does not resolve the Hubble tension. The tension demands new fundamental physics. A follow-up study retested the void hypothesis with direct distance tracers, and found that the data prefer a void approximately 10% the size of the original fiducial model, narrowing the case without eliminating it. Several alternative resolutions have been proposed within or beyond lambda CDM, none yet conclusive. Some of the ideas being explored: early dark energy active before recombination, additional relativistic species, interactions between dark matter and dark energy, and modifications to gravity. Recent baryon acoustic oscillation results have hinted that dark energy may be evolving over cosmic time. The data are suggestive, not yet definitive. If true, this would itself be a major modification to lambda CDM, independent of the void question. One team has proposed that an alternative theory of gravity called MOND, supplemented with sterile neutrinos, could reconcile observations. This view is not the consensus, and most cosmologists remain committed to lambda CDM. The European Space Agency's Euclid satellite is conducting a survey designed to measure weak lensing and galaxy clustering with percent-level precision. Its primary cosmological results are expected from 2026 onward. The Vera Rubin Observatory will begin the legacy survey of space and time, a decade-long survey of the entire visible sky. It will dramatically improve the local galaxy density map and the supernova distance ladder. The Nancy Grace Roman Space Telescope will further constrain dark energy evolution and cosmic structure at the scales relevant to the void question. The KBC void question remains open, whether we are genuinely inside an extraordinary structure or whether lambda CDM cosmology needs revision, or both. No single instrument has yet delivered a verdict. We appear to sit near the center of a vast underdensity 2 billion light-years wide, a sparser-than-average bubble, a cosmic neighborhood quieter than the universe at large, and the instruments still point outward, waiting for the numbers to come in. A line of stars, faint and final, drawn across the dark. Tonight we trace the outline of a hole, 2 billion light-years wide, mapped its edges in infrared and X-ray light, counted the galaxies that should have been there, and found only half as many as the standard model predicted. We followed the numbers to a simple fact: the universe around us is quieter than it should be, and we asked whether that silence might explain why two ways of measuring the same expansion rate refused to agree. Some of you stayed awake through every redshift bin. Some of you drifted long ago. Both journeys mattered. You are here, inside the sparse bubble we call home, where the stars are farther apart than average and the clocks still disagree. the dark will still be here. So will I. Come back tomorrow night, and we will map something else together.